Hello everyone, welcome to this video. Today we're going to be doing two problems from Griffiths Introduction to Quantum Mechanics. These problems are meant to practice a little bit what we have already seen from the quantum harmonic oscillator. The problems are problems 2.11 and 2.12 from the third edition of the book. Now, I did change the wording of the problem a little bit because since I'm going to be speaking here, I can explain a little bit more. So the titles that you see here are not the same as in the book, but the idea is going to be the same and we should get to the same results. So problem 2.11 asks to show that the lowering operator cannot generate a state of infinite norm, which means that if you take do this normalization process of a state on which you operated this lowering operator, then you should get something that is finite. And that should be true if the state itself is a normalized solution to the Schrödinger equation. So basically what we want to do here is just take a look at this quantity. Whoops, I forgot to put the psi in there. Okay, to the quantity A minus acting on psi. Okay, and we take the norm of this thing. So let us just see what we get from this. So this is the same as we should know by now of A minus psi conjugate times A minus psi dx. So now let us write for this A minus the definition of the operator, but it's going to be conjugate. Okay, so the operator is going to be h bar divided by I. Yeah, I'm going to conjugate it in a few seconds. D by dx of psi conjugate, it's going to be minus I m omega x psi conjugate. Okay, so since this has to be conjugated, there should be a minus sign in here, and this minus sign should be a plus sign. Okay, so now we accounted for the fact that it's this A minus is now conjugated. Okay, so now we just leave the other one be. And in order to continue, what we're going to do is that we are going to put this in here. So we're just going to multiply this bracket out. So we get minus h bar over I d psi conjugate by dx times A minus psi plus I m omega. Oh, I forgot the 1 over square root of 2m. Sorry about that. I'm going to put it right here. I m omega x psi conjugate A minus psi and dx. Okay, so what we want to do now is just take a look at this right here. This integral we can do by parts, so let's call it just I1, and from there we can declare that our u from the integration by parts is going to be the thing that we can easily derive, which is just going to be A minus psi. So du is going to be d A minus psi dx, and dv is going to be the thing that we can easily integrate, which is just d psi conjugate dx. So v is going to be psi conjugate. So with that, we can now rewrite this integral I1, which is, remember, just this thing over here, as A minus psi conjugate psi minus the integral. I didn't put the limits here just now, but remember the limits are from minus infinity to infinity. I'm going to just add them here. So this is going to be evaluated between minus infinity and infinity. And this integral right here will be psi conjugate d A minus psi. Oh, there should be a dx here, by the way. Dx, dx. Okay, so this term right here is 0 because both psi and psi conjugate are 0 at infinity and at minus infinity, because our wave has to be normalized, right? So if this psi is itself normalized, then at both infinity and minus infinity, it will have to be 0. If you don't understand that, then go back a few videos where we talk about normalization, and we made a little sketch so that it can be a bit clearer. And what we are left then with is with this I1 right here. So what I'm going to do is just go to the next page and plug it into this initial integral. So what we had was the integral 1 over square root of 2m from minus infinity to infinity. And this first term, we had this minus h bar divided by I, and now comes the result that we just got, which was minus psi conjugate. Was it that way? I don't really remember. Let me see. It was, yeah, minus psi conjugate d a minus psi dx. What else? Was there anything else? No, that was it. The dx is just going to be on the end. And then we had the second part, which was I m omega x psi conjugate a minus psi. Yeah, I think this. Oh no. There we go. I'm just making sure that I got enough parentheses everywhere. Okay, I think I put some of these parentheses were unnecessary, but it doesn't matter. Okay, so now let's put this psi conjugate in front and this a minus psi to the right. So get 1 divided by 2m integral of minus infinity to infinity. These minus will cancel each other out, so we just get h bar divided by I. We are going to put this psi in front, as I said. So it's going to be multiplying h bar I d by dx plus I m omega x, and this is going to be multiplying a minus psi dx. So right here we have the a plus operator, so we can now write this as minus psi integral from minus infinity to infinity of psi conjugate a plus, which is this right here, and considering this 1 over 2m, of course, times a minus psi dx. But what is this right here? From the previous video, I think it was a previous one, yes, we saw that a plus a minus acting on psi was just the energy minus h bar omega divided by 2 acting on psi. So we can now rewrite this as the integral from minus infinity to infinity of psi conjugate e minus h bar omega divided by 2 psi dx. And we can just take this out of the integral because it's just a constant. So we get e minus h bar omega divided by 2 times the integral from minus infinity to infinity of psi conjugate psi dx. But as we saw before, and as we discussed, this is just the normalization of psi, and we said this wave function is normalized. So this is just 1, so we can just erase it. So this is our result. Okay, so what we saw was that this integral from minus infinity to infinity of a minus psi squared dx. Okay, so this is our result, and as we can see, this is indeed non-infinite. It's finite. We get e minus h bar omega divided by 2, and we can even put in the result for e, because remember, e of some n is just going to be n plus 1/2 times h bar omega, right? So you can see this is finite. It will have to be an infinite n in order for it to be infinite, but n is not going to be infinite, so there is no problem there. So in the same way we did this, you could show that the integral from minus infinity to infinity of a plus psi squared dx is going to be e plus h bar omega divided by 2. Now, I thought about doing this explicitly, but it's literally the exact same thing that we did, and what I think I will do is just go back here and show you what would change. So let's say we want to find now this for a plus. So this here is now a plus, this is going to be a plus, and this is going to be a plus. Here it's going, this part is going to be the same, but this plus sign will now be a minus sign. This will be a plus. Right here, this will be a plus. This here will be a minus. This is gone. This is a plus. This whole integration by parts thing is going to be the same, except obviously with a minus replaced by a plus. And then when we go back into the integral, this will be a plus, this will be a minus, this will be a plus, and in the end, this here will be a minus and a plus. So what we will get is that this right here is just a minus, so this here will be a minus, this will be a plus. So when we replace the Schrödinger equation written in terms of operators, we will have, instead of a minus, a plus, a plus, a minus, we have a minus, a plus. So it's going to be this. So we're going to do, it's literally exactly the same as we just did, but there's going to be a minus sign in between. That's it. So that is why I decided not to do it explicitly, but I hope that if you weren't sure how to do it, at least going over it quickly would help you some way. Okay, so that is problem 2.11 from Griffiths' book. Now let's take a look at the problem 2.12. Sorry. So this problem states the following. It says, the raising and lowering operators generate new solutions to the Schrödinger equation, but they are not correctly normalized. Thus, a plus psi n is proportional to psi n plus 1, and a minus psi n is proportional to psi n minus 1, but we would like to know the precise proportionality constants. So what this means mathematically is that a plus psi n is not just going to be psi n plus 1, but it's going to be some constant, let's call it c plus, times psi n plus 1. Okay, and once you multiply by that constant, then psi n plus 1 is going to be normalized. But if you do not multiply by that constant, as we saw, it's not going to be normalized. And in fact, this part is very related to what we saw in problem 2.11. That's why I didn't want to make separate videos about this. And similarly, a minus psi n is not going to be just psi n minus 1, but it's going to be some constant c minus times this state. And the way to find this is basically to do what we did before. So let's say, okay, we want to just normalize our state, which would be now a plus psi n squared. So this is, as we just saw, this is just going to be E plus h bar omega, and not just E, but En. Right? Now we want to emphasize that it's going to be the energy of a certain energy level. Before, it wasn't really necessary to emphasize it, so we just wrote E, but now we want to make sure that we emphasize that. And in fact, we can now rewrite the expression for E, which is just N plus, oh, this is supposed to be divided by 2. Did I write it correctly before? Yes, I did. Okay. Whew. Phew. I don't have to restart the video. Nice. Okay, so it's N plus 1 h bar omega, half omega plus h bar omega divided by 2. Okay, so I just wrote here the expression for En. So when we now add this up, we get N plus 1 h bar omega. But on the other hand, we know that this is going to be, if we let a plus act on psi n, as we saw here, it's going to be c plus times psi n. So we can now separate this constant, so we get c plus squared times the absolute value of this psi n squared dx. But this psi n is normalized because, as we see, when it was normalized by this normalization constant, it's normalized, so this will just be 1. So we get that this is just c plus squared. But this is the same as we had up here. These two things are the same. So we can now set c plus squared equal to n plus 1 h bar omega. So from here we see that c plus is going to be the square root of n plus 1 h bar omega. Okay, so that is a very important result, because that will give us the normalized states when we apply this raising operator. So now we're going to do basically the same thing, but with the lowering operator. So I'm going to erase this right here so that I have space. Okay, so let's do it now with a minus. So let's now normalize. Whoops, I did not want to change colors here. Okay, so a minus psi n. When we normalize this is going to be, I'll do it in the different order now, just to make sure that we understand this well. This is going to be the integral of some constant c minus times the state psi n minus 1. I did write psi n plus 1, did I? I hope I did. If not, back when I said a plus psi n, this is going to be c plus psi n plus 1. Okay, I'm not sure if I wrote psi n plus 1 or if I still said psi n. I really hope I didn't make that mistake. Okay, well, continuing. C minus psi n minus 1 squared dx. And here we can, as before, just separate this constant from this integral, which will now be 1. So we see that this expression is just c minus squared. But this, as we saw in the previous problem, is just n h bar omega. I think I'm going a bit too fast there. Last time we saw that it is e minus h bar omega divided by 2. So when we write the expression for en, we get that this is going to be n plus 1/2 h bar omega minus h bar omega divided by 2, which is just going to be n h bar omega. I kind of skipped that without wanting to. And this is going to be c minus squared. So c minus is just going to be n h bar omega in a square root. Okay, now there is an extremely important comment that I have to make, because something that really confused me when I was doing this for the first time is that in books such as Griffiths, they put like this I in front, or minus I don't really remember well. So, and I didn't understand why I was getting the result without the I, and they just said that it was there because this state has to be a real function. But I didn't really understand that. But the thing is, because this is going to be, you're just going to take the norm of this, and the norm of I is 1, this doesn't really change anything physically. It's basically just a phase, and phases here in this topic don't really make an observable difference. So the reason Griffiths did that is mainly because of convenience, and because that is a way that was probably more intuitive to him. But these forms are equivalent with and without the i's. So just in case you were having the same question or the same doubts that I had, I hope that can clear it up for at least some of you. Okay, so this is part A. Now comes part B, which is basically the reason we were doing all of this in the first place. We want to now use this to determine the normalization constant an, and this an is basically the an in this generalized form for any wave function that we had found in the previous video. So the way to do that is first to realize that this thing right here is because the first state, the ground state, was just some normalization constant times e to the minus m omega divided by 2h bar x squared. So this thing right here is just psi 0 divided by a0. So we can replace this exponential for what we just found. So psi n of x is going to be an, a plus to the nth power, times psi 0 divided by a0. Okay, so that's our first step. I'm going to erase this and put all of this just a little bit further up. Okay, so now we're going to, well, I'm also going to put this a0 at the front because it's just a constant and it doesn't really make sense to have it there. So now we're going to let one of these operators act on psi 0. So I'm going to leave this as an divided by a0 times, and now since we took one of these operators out, it's only going to be n minus 1. Okay, because one of them is now here. So when this a plus acts on psi 0, it gives us the first excited state. Okay, so it gives us psi 1, but remember, this is not properly normalized. We have to put here n. Okay, I need more space. I did not calculate this well. This is going to be n plus 1 h bar omega psi 1, and well, the square root of this right here. But what is n? N was 0, because 0 is the state that we applied this operator to. Do not be confused. N is the state to which you applied this operator. So in this case, it was 0. That's why it doesn't make sense to have the lowering operator on the 0th state. Okay, so don't put a 1 in here, please. That's a common mistake. Please don't make that mistake. Okay, so we get now, and I just made that mistake. We get just 1 times h bar omega. Okay, so let us do that again. So we're going to have a n a0 times the square root of h bar omega times a plus to the n minus 2 power, and now we put that a plus that we took in here with psi 1. Okay, so there's nothing illegal going on. So a n a0 square root of h bar omega times a plus n minus 2. So let us look what happens here. Once again, we get the square root of n plus 1 times h bar omega times psi 2. Okay, because we applied the raising operator. So this n is now going to be 1. So this whole thing is just going to be the square root of 2 h bar omega acting on psi 2. So now we can once again do the same thing. So we get square root of h bar omega times the square root of 2 h bar omega times a plus n minus 3, because now we took another one, a plus, and we're multiplying it with our, or making it act upon psi 2. So I hope that now you're going to see where this is going. This right here is just going to be square root of 3 h bar omega psi 3. So what we are going to have here is just a n a0 square root of h bar omega square root of 2 h bar omega square root of 3 h bar omega. And if we continue to apply this a plus, we are going to be able to do it until its exponent is going to be 0, because then we are not going to have any a plus left. So we can do this dot 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 until at some point we have applied it n times. So our last term will be n h bar omega. Okay, so at that point we are going to be at our state psi n, and we just cannot go any further. And remember, this expression is for psi n. Okay, so in order for these two things to be the same, we need that the interior here has to be 1. So this here has to be equal to 1. So in order for that to happen, let us see what we must do. So this copy it. There we go. Okay, I didn't want to copy the line underneath, but whatever. I'll just delete it. Okay, so this has to be equal to 1. So now we can just solve this for a n. So we get that it's going to be a0 divided by this expression. But if we see, we get h bar times 2h bar times 3h bar times so on and so forth until nh bar. So this is basically just the square root of n factorial times h bar omega to the nth power. Okay, so now all we have to do is find this a0 constant. So this a0, remember, is the normalization constant of the ground state of the harmonic oscillator. So let us normalize this. So when we do that, we get that 1 has to be equal to the integral from minus infinity to infinity of a0 squared times this e to the minus m omega x squared divided by 2h bar squared. But when you square it, you're just multiplying the exponent by 2. So that 2 is going to cancel out the 2 in the denominator. Okay, so that dx. Now this integral is a Gaussian integral. So that integral, I hope you have seen it before. If not, the result is known. I don't think you can integrate it by standard means. It has to be done numerically. So the result from that, just in general terms, if you have an integral from minus infinity to infinity of e to the minus bx squared, this is going to be the square root of pi divided by b. Okay, so now we're going to use this result, and it's very good if you learn this, because this shows up very, very often. So it is good to know. So this is going to be a0 squared times the square root of pi divided by b. But what is b in this case? It's m omega divided by h bar. So the h bar is going to come up here and m omega, right? Since we're dividing by our quantity b. So from this we can see that a0 squared is going to be, if we now divide by this, it's going to be m omega divided by pi h bar to the 1/2 power, and taking the square root of this, we get that a0 is just m omega pi divided by h bar to 1/4 power. Okay, so let's put this now back into our formula for an. So we're going to see that an is then m omega pi h bar to the 1/4 power, and this is going to be multiplied by 1 divided by the square root of n factorial h bar omega to the nth power. Okay, so this is the normalization constant that we were looking for. I hope that you were able to follow through on the video. If you did, and you have any sort of questions, just let me know in the comment section. If you liked it, make sure to like the video. It really helps the YouTube algorithm. So I'll see you next video, where we will do some more problems on the same topic. See you later.